In the name of God, I want to talk about high-dimensional parametric modeling for longitudinal data. This is a joint work with my doctoral student, Dr. Miss Talboni. Uh, I will start with an old problem for the motivating example. It's a kind of ACE data, and but we will propose a new model, and we will also consider the underlying assumptions. So this data is the motivating example. We will consider the trajectories plots, and we try to pave the road for model. Then we will propose the new model, which is a penalized, generalized parametric longitudinal model. And then we will consider a little bit about theory and also the application of the work. Okay, the data contains too many observations of CD4, cell counts on 369 men infected with the HIV virus. Then the response here is the number of CD4 cells. And this is a very old problem, which is considered in many mixed longitudinal studies, especially mixed model longitudinal type of work. But in none of the works, they consider the Poisson distribution, which we consider Poisson distribution as the underlying distribution for the response. Uh, we've seen that in many studies, even in base studies, and which is publishing good journals, uh, which are publishing good journals, they consider the logarithm or square root of the response variable, and they assume it is normally distributed, which is not correct. And we tested with our software, and we found Poisson distribution fits better than normal, and normal doesn't fit actually. So here the response is in a number of CD4 cells. We do not make any logarithm, any transformation of the data, logarithm or square root. The predictive variables are listed here, which the focus is the year. And here we consider the year to be a non-parametric component in our study. Okay, this is the trajectory plot for the CD4 data. Uh, the observed evolution is displayed in gray. And this is the year which you consider it performs non-parametrically, or is better. It doesn't affect the response linearly. So this is a starting point. We have a set of longitudinal data. We consider a count model for response variable. We also consider a mixed model and take the intercept as the fixed covariate. As I previously showed you, the non-parametric component is the year here. We also intend to do a model selection procedure, or we want to significantly select the variables with the automatic selectors. And finally, we consider a high dimensional setting in which the number of variables goes with the number of samples. This is the theory part of the work. So the work is totally new. Although we consider an old data set, but it's for demonstration only, and we show that it is important that we check the underlying assumption for the response variable in our modeling. Okay, this is the formula for the response. We consider it to be exponentially distributed, and we consider a generalized linear type of modeling. Further, since it's a kind of mixed model, we have a random effect component, which we show it with U here, and we assume U follows the specific distribution, which in the numerical part, we consider the normal distribution. So the assumption is a function of the mean of the, or better said, the systematic component of a model in the generalized linear setup or setting has a fixed component, has a random component, and also a non-parametric component. Here, I must also mention that the number of variables which is dependent to the fixed effect component grows with n. So we consider high dimensional setting under this assumption. Then we have one non-parametric component, and here the random effect part is not related to P, which high dimensional part does not refer to this part of the model. So the high dimensional part is specifically referred to this part. Okay, naturally we use spline to approximate an arithmetic component, which we also use it here. So we use B-spline to approximate an arithmetic part, the, the f function, and the design is now changed. We have the fixed component as already we had it. Again, the random effect part, and then the non-parametric, which we approximated with B-spline. Now, if we combine these two together, the x part and the b part, then we can term it as D. So the matrix D consists of x and b, and the vector parameter theta is related to beta and alpha, which is the parametric part of the B-spline approximation. Here again, I emphasize that the number of parameters in alpha for the non-parametric part is Hn, and then number of components in beta for the fixed effect part is Pn, which we consider Pn to be greater than n. Okay, this is the whole model. The response, the random component, it is a generalized type of modeling, and then the systematic component is summarized with this equation at the end. Further, we can since it's kind of high dimensional analysis, we would like to select significant variables, and we use automatic selectors. So we consider the parallelized log likelihood. So I must also emphasize the work is based on likelihood, and we will consider a generalized estimation equation. The penalized form is given by this, and since the coefficient theta, which is consists of beta and alpha, the fixed component parameters and the non-parametric component parameters in which we obtain in the approximation depends to the first and third term, which and we propose the penalized estimated equation by this formula that you can consider here. The S matrix is given by this. We will use this S further on in our analysis. We specifically use scat penalty due to Fang and Lee, and because it has good performance, and the results are given for scat penalty, so we will consider the derivative of scat to be given by this formula. Okay, also proposed estimator for theta is the solution of u theta n equal to 0. This is the penalized estimator equation that we propose. But formally, because of discontinuity, we do a kind of approximation, and we consider the approximate solution in which u theta hat is of small order. Further, we also consider for non-parametric component to be approximately of this order. These are for computational sake. We take the well-known A in SCAT to be equal to 3.7, and also we use the GCV for the selection of the tuning parameter penalty part. I will quickly go through a small theory of the work. In order to do some theoretical derivations and also prove the oracle properties, we factorize beta naught to beta naught 1 and beta naught 2, and then the true parameter case here is factorized into 3 disjoint sets. We also make some other assumptions. Accordingly, the design is divided by di1 and di2 in order to point to beta naught and beta naught 1 and beta naught 2. Further, we assume only a small number of covariates contribute to the response, which we actually considering a sparse kind of modeling. So we assume sparsity. Also, since it's high dimensional and p is greater than n, or better say Pn is greater than n, we assume log Pn has this order, and also some other assumptions which we use for the proof of our results. However, I don't propose to give the proofs here. The first theorem, which is very important in considering generalized equation estimating equations is the existence of the solution. Here we have we've proved the existence for the high dimensional setting, which you will see k varies from this point to Pn. In the other theorem, we show that the proposed results are consistent, and we must further consider that Pn goes to infinity, but it's slower than square root of n. And in the other result, we show the oracle property, which we can significantly select the uh, or better say, almost sure we can select the significant variables and also the asymptotic normality of the estimates. Okay, if you want to see the proofs of the theorems and also for extensive simulation study, I refer you to the archive version of this paper, and I quickly go to the real data application. Again, we involved with ACE data. If we have a total number of 2,376 observations, we let year to be modeled non-parametrically, or better say, year is not related linearly or affect linearly the response. And we use the scat penalty, and the tuning parameter we obtain from generalized cross validation is equal to 0.45. This is the result. This is the proposed model result, and it shows that, for example, age does not contribute to the response, which is very new. It also, and according to the theory part, we can rely on the result that the solution exists. It is consistent. So consistently, we can say age does not contribute. And this is very surprising result, because whenever you refer to doctor, he will ask about your age. So it's very important we do not, take age as covariate in our analysis. And you see the STs of or estimates are better than the other estimates, which we considered for comparison's sake, the generalized semi-parametric mixed effect model and also the penalized generalized linear mixed model. So here, and finally, I want to mention that the AIC BIC of our proposed model is better than two competitors. We also consider the R square, and R square was high, which I didn't report it here. So in summary, if I want to wrap what I've proposed, we developed a general methodology for simultaneously selecting variable and estimating the unknown components in semi-parametric mixed effect model for non-normal longitudinal data. Luckily, our model beat the other models, and we approximated the non-parametric component, the B-spline. But for future work, it is very nice to mention two things. First of all, it is not easy to count the CD4 cell data. So we were working on the other covariates and also responses that can be replaced with CD4 data. And also in other work which we are busy, which is close to varying coefficient type of modeling, we want to consider more variables than just one variable for a non-parametric component, and we will consider the additive type of structure for our high dimensional proposal. Thank you very much for listening to my talk. If you have any question, you can ask me in the discussion.